All right, ladies and gentlemen, this is going to be review video number 18, separation of solutions and how to do it. So the two main methods we'll be learning about are going to be chromatography and distillation. So let's start with chromatography. What is it? It's basically just a method used to separate a solution into its components, and that separation is going to be based on the strength of the intermolecular forces within that solution, or basically polarity, and then molecular size. So larger molecules are going to move a little bit slower because they're heavier and they're going to be harder to separate using this method. In chromatography, there's going to be two main parts of a chromatography setup. We're going to have a mobile phase, which is the part of the chromatography setup that is going to move along with the sample that's being separated. And we have a stationary phase, which is the opposite. It's the part of that setup that does not move with the sample that's being set up, which, again, that doesn't really make sense because you haven't seen the setup yet. But what we're going to do in class is we're going to do a form of chromatography called paper chromatography, which is one of many possible chromatography setups, but paper chromatography specifically is geared towards separating components of an aqueous or liquid solution from one another. And you're pretty familiar with aqueous or liquid solutions so far, like salt water, sugar water, inks, any of that would be comprised of aqueous or liquid components, right? So with paper chromatography, like what we're going to do, ink is going to be the most common solution being separated using this technique. And the reason for that is because when you use ink in paper chromatography, it's really, really easy to see the different parts of that solution because ink is often made up of several dyes that when mixed together have one color, but you can actually separate them. And you're all kind of familiar with that because if you've ever used a pen and then gotten the paper that pen on is wet, you know that ink is going to bleed all over the place. All right? So different components of ink are going to have different polarities, right? Especially if that ink is made up of several different colors together. Some of those colors might be made up of chemicals that are a little bit more polar. Some of those ink components might be made up of chemicals that are less polar. And so in paper chromatography, the solvent that you're using, typically water, though it's not always water, is going to be your mobile phase. And what that's going to do is when you expose that solvent to the ink, it's going to pull some of that ink along. Specifically, whatever type of solvent you use will pull molecules that are like itself along. So if you're using water, we know that water is a polar molecule, right? You're familiar with that. So if we're using water, water is going to pull the polar parts of ink along with it. But if you're using a non-polar solvent like, I don't know, hexane or propane or like any of those hydrocarbons that tend to be non-polar, they're going to pull along the parts of the ink that are more non-polar instead. The paper in paper chromatography acts as the stationary phase. And that should make sense because paper is a solid and it doesn't really move around at all. But the other thing about paper that you need to understand is that it is weakly polar. Paper is not non-polar, nor is it super polar. It's kind of weakly polar, meaning that it's going to be less polar than a polar solvent like water would be, but it's going to be more polar than a non-polar solvent like hexane would be. So whatever doesn't get pulled along by the mobile phase or the solvent is going to stick to the paper instead. So let's look at an example of paper chromatography when we're using a polar solvent. And in this case, our polar solvent is going to be water. All right, so we would put an ink spot here on a piece of paper, and then we're going to dip that paper into the water. Water, in this case, is going to represent the mobile phase of that paper chromatography. And again, paper is going to represent the stationary phase. So after we dip that end of that paper in the water is going to start moving. It's going to start diffusing up the paper. And as it does that, some of this ink spot is going to get pulled along with it, specifically the part of that ink that is going to be the most polar. And I know that it's the most polar part that's going to get pulled because water is a polar molecule, so it's going to pull polar things with it. So if we let that ink on the paper sit in the water for a little while, after that water has moved all the way up to the top, we're seeing now a spread of different colors that have been pulled out of that ink. We're seeing yellow up here, we're seeing red, orange, blue, what looks like a pink or a purple down here, so on and so forth. Everything that ends up at the top is going to be most polar. And I know that it's most polar because we used water as a solvent, and water is really polar, so it's going to pull the most polar things with it. Everything that kind of hung around at the bottom and did not really move very far is going to be the least polar. Right? So that's how it's going to work if you're using a polar solvent like water. However, if you use a different solvent in paper chromatography, like say oil, for example, now your solvent is oil and it is non-polar, but that doesn't change the fact that that solvent still represents the mobile phase. And it doesn't change the fact that paper is still your stationary phase. What it does change is what's happening with the ink. Because again, if you put this ink in the oil and you dip it in a non-polar solvent, suddenly the thing that's dissolving or moving up the paper is no longer a polar thing. It's a non-polar thing. So what it's going to pull with it to the top is actually the least polar stuff. And that's specifically because oil is non-polar. Now down at the bottom, the stuff that didn't move very much is going to be our most polar stuff. And this is all relating back to the principle of like dissolves like, right? Polar solvents are going to dissolve polar solutes, and so they're going to pull those polar solutes along. Non-polar solvents are going to dissolve non-polar solutes and therefore pull non-polar solutes along. And that's basically just the principle of paper chromatography, is literally just like dissolves like. All right? The other method of separating a solution that I'd like to talk to you about is distillation. And that is a method that is going to separate the components of a solution based pretty much solely on the strength of their intermolecular forces, and it's going to use heat to do that. So, if you heat a solution, substances that have weaker IMFs, like LDF, London dispersion forces, are going to have lower boiling points. However, substances with stronger IMFs are going to have higher boiling points, and that's something you should already be familiar with. If that substance in the solution is an ionic or a network covalent substance, that thing is going to have a very extremely high boiling point. And so basically what's going to happen is, as I heat a solution, stuff with weaker IMF, stuff with lower boiling points, is going to boil off very quickly, and it's going to leave behind things that have higher boiling points. So this is a basic distillation apparatus. So in here, in this little round bottom flask, you have your solution. And right, our solution is a mixture of a bunch of stuff. So if I want to separate that using heat, if I have components of my solution that have different boiling points, I can boil one of the components of the solution off up here, and it's going to travel all the way through this tube and come down over here as something called a distillate. But what's left behind in here after that process is done is the higher boiling point stuff. And the lower boiling point stuff is over here. So the only thing that you really have to keep in mind in this setup is that the stuff left behind, yes, it has a higher boiling point, but that means that the stronger IMFs are over here, and the weaker IMFs are over there. So like, let's say I was trying to separate a solution of CH3OH and CH4, for example. I'm just going to draw out the Lewis structure so you can see what I'm talking about. All right, so let's say that we have a mixture, a solution of those two things. This thing over here is nonpolar. This thing over here is polar, right? So looking at that, I know that the nonpolar part of that solution is only going to be able to do London dispersion forces, which is weak. However, I know that this thing over here, since it's polar and it has this OH group on the side, that thing is going to be able to hydrogen bond. So this thing has stronger intermolecular forces. So if I want to separate those two and I stick the solution of those two things into this distillation apparatus, the thing that's left behind over here is going to be CH3OH because that's going to have a higher boiling point. The thing that makes it over here is going to be CH4 because that thing has a lower boiling point. And that's how that separation is going to function. If you're not sure how to interpret things like that, please feel free to ask me some questions about it in class.